Today we will be starting a topic called relations. Now, we know we come across this word very often, like when we write somebody's name related to us, then we have to write what is the relation of myself to that person, like that person can be my father, mother, brother or sister, like that. In that way, there are other situations like when we look at students. To each student we relate a number which is which may be the enrollment number. Then to each person we often relate mobile numbers or many other numbers. Now, we will be looking at these things more systematically. So, we will be talking about sets of objects. For example, let us consider a situation where we have a set of students. Suppose S is equal to the set of students and N the set of enrollment numbers. Now, we know that given a student S belonging to this set S, we will have a number, let us say n, belonging to n, such that this n is the enrollment number for the student S. In this way we can write a list. Similarly, we can consider the set of names of students. Maybe we can write the set as T, the set of names of students, and again n the set of enrollment numbers. Now, for each name, let us say T belonging to capital T, there is an enrollment number. For example, that number may be n belonging to capital N. Now, here we see that we may have the same name associated to different enrollment numbers, because there can be different students having the same name. So, we can have many such possibilities. So, here we see that naturally we are arriving at a situation where objects belonging to two sets are related to each other. We would like to look at this more systematically, and therefore, we will first go to a mathematical definition which is called Cartesian product. Now, if we have two sets A and B, the Cartesian product of these two sets is denoted by A cross B, and it is the ordered pairs of elements of A and B. We will write this as this. This is the notation of a set, and it contains all ordered pairs A B, where A belongs to A, capital A, and B belongs to capital B. For example, let us consider A to be the set 2, 3, 4 and B to be the set 4, 5. Then the Cartesian product A cross B is 2, 4 2 5, 3 4, 3 5, 4 4 and 4 5. We can go the other way around. We can have Cartesian product of B and A, write it as B cross A, and we get 4 2, 4 3, 4 4, and then here 5 2, 5 3 and 5 4. Now, we consider the case when the sets are not distinct. We can have Cartesian product of the same set over and over again. So, we can have A cross A, which is the Cartesian product of A with A, and we will get 2 2, 2 3, 2 4, then 3 2, 3 3, 3 4 and 4 2, 4 3, 4 4. Next, let us look at some examples of Cartesian product. Let us consider the set R, which is a set of real numbers. The Cartesian product of R with itself is often written as R square, and this is set of ordered pairs of elements of R. So, we have pairs like x comma y, where x and y both are in R. Now, if we go back to our usual school geometry, then we will realize that this is nothing but the real plane of which we use in coordinate geometry. Now, we can modify the set R a little bit, and we can get R plus, which consists of set of all positive real numbers. Now, if we have this set of positive real numbers, then we have Cartesian product of R plus with itself, and we will get again all ordered pairs, but in this case these ordered pairs are such that both the elements are greater than 0. Therefore, we will have the first quadrant of the plane. Now, let us look at the situation over here. So, here we have set of positive real numbers starting from here going up here, and another copy of the same set over here, and R plus cross R plus consists of points in the shaded region. Now, we come to the formal definition of relations. If we start with two sets A and B, which need not be distinct, any subset of the Cartesian product of A and B is said to be a relation from A to B. And similarly, if we consider subsets of B cross A, then we will get relations from B to A, and if both the components of the Cartesian product are same, that is, if we have A cross A, we write in short A square, then also any subset of A cross A will give us relations technically from A to A, which we usually call relations on A. Now, let us suppose that we have a relation R from A to B. In other words, we have a subset R from of A cross B, and now we will take an element A belonging to A and an element B belonging to B, and we will say that that A is related to B if the ordered pair A B belongs to R. The fact that A ordered pair A B belongs to R is alternatively written as A R B, and in fact, in the context of relations we will be very often writing A R B instead of ordered pair A B belonging to R, because it is more convenient and it is more intuitive, because it tells us that A is related to B. Now, we go to some examples of relations. Let us consider two sets again, A 2 3 4 and B 4 5. Now, let us look at the Cartesian product of A and B. So, we have A equal to 2 3 4 and B as 4 5. Let us check that once. A is 2 3 4 and B is 4 5. The Cartesian product of A with B is the whole set 2 4 2 5 3 4 3 5 4 4 and 4 5. Okay. We will consider some subsets of this Cartesian product. The first of all, the subset which contains nothing, which is denoted by this symbol and read as phi, then the subset 2 4 2 5, then the subset 2 4 2 5 3 5 4 4 and A cross B itself, because A cross B is of course a subset of itself. Now, all of them are relations from A to B. Phi is said to be the empty relation because it contains no element. That means, with respect to phi, no element of A is related to B. On the other hand, the other extreme case is A cross B, which contains everything. If you pick up any element in A and another element in B, it definitely is in A cross B. So, it is related. And then we have intermediates which are in fact more meaningful. So, we have 2 4 2 5, that means 2 is related to 4 and 2 is related to 5 and nothing else, no other elements are related. Then 2 4 2 5 3 5 4 4. This is another relation where we have 2 is related to 4, 2 is related to 5, 3 is related to 5, 4 is related to 4, and that is all. So, these are relations on A cross B. Now, we look at other relations. We go back to the set which we were discussing a while back. So, we consider Z plus, which is a set of positive integers, and we consider a relation R on A, which is in fact Z plus, which is given by all ordered pairs of x y in case x is less than or equal to y. Now, this means that given two elements in Z plus, that is positive real numbers, I have to compare them. suppose I have got two elements a x and y, I pick them up, and if x is less than or equal to y, I say x is related to y. I may write x comma y belonging to R, or x is related to y, and if they are not related, then they are not related. They will not be related if x is greater than y. We can in fact draw a graph here. So, suppose this is 1, 2, 3, 4, 1, 2, 3, 4, then we have 1 is related to 1, 1 is related to 2, 1 is related to 3, 1 is related to 4, and so on. Now, starting from 2, 2 is related to 2, 2 is related to 3, 2 is related to 4, and so on. 3 is related to 3, 3 is related to 4, and so on. 4 is related to 4, 4 is related to 5, and so on. We go to another example. Now, this is an example consisting of a set and power set of that. By power set of a set, we mean the set of all subsets of that set. Let us look at the examples of some power sets now. Suppose we have the set S which is equal to 1, 2, then the set of power sets of S is written as P S, which is equal to phi, that is the empty set, then 1 which is the singleton containing 1, then 2 which is a singleton containing 2, and 1 2 which is the whole set. So, this is the power set of 1 2. Then we can consider S to be equal to 1 2 and 3, and the power set of S is phi, then 1, then 2, then 3, then we will have 1 2, we will have 1 3, and then we will have 2 3, and ultimately we will have the whole set 1 2 3. Now, within the power set, we can consider a relation defined by the set containment. That is, we will say that two sets A B belonging to the power set of S are related if A is contained in B. Now, let us look at the slide. We have A B belonging to the power set of S. We define the relation R on P S by A R B if and only if A is a subset of B. Very often, instead of writing R, we will simply write the subset equal to notation. Now, suppose we consider the set S, then as we have seen that the power set of S is phi 1 2 and 1 2, and the containment relation is phi phi, phi 1, phi 2, because phi is a subset of 1, phi is a subset of itself, phi is a subset of 1, phi is a subset of 2, phi is a subset of 1 2. Then if we when we start with 1, 1 is a subset of 1, 1 is a subset of 1 2. Then we start with 2, 2 is a subset of 2, 2 is a subset of 1 2, and eventually 1 2 is a subset of the set 1 2 itself. So, this listing gives us the relation defined by subset subset equal relation. Okay. Next, we now take up another relation. Our underlying set is now the set of integers, and we define a relation which is commonly called the divisibility relation. We write the relation by the symbol a vertical straight line. We call this relation, which is which we denote by a vertical straight line on Z, as follows: A B belonging to Z. For A B belonging to Z, A the straight line B, if and only if A divides B. So, we will commonly say that A is related to B if A divides B. For example, if we consider 2 and 6, then of course 2 divides 6. So, we will write 2, then the vertical straight line and 6. But if we compare 3 and 5, 3 does not divide 5. So, we will write 3, then the straight line and the cancel, and 5, which we will read as 3 does not divide 5. Next, we will take up another relation which is extremely important in mathematics and computer science. This is called congruence modulo relation. But to understand this, let us start with some examples. Here also we consider the set Z, which is the set of all integers, then let us pick up a positive number, that is a positive integer. So, let us pick up 7. Of course, 7 belongs to Z, and we pick up 2 integers and take their difference. We will say that these 2 integers are congruent modulo 7 if their difference is divisible by 7. For example, if we consider 14 and 28, let us see what happens. Let us say x is equal to 14 and y equal to 28. Y minus x is 28 minus 14 is equal to 14, and it is of course clear that 7 divides 14, and therefore, we will say that x, that is 14, is congruent to y modulo 7, and we will write it as x y mod 7. We will read as x congruent to y modulo 7. Now, we see that there is nothing special about this 7. We can take any integer, any positive integer m, and we define the same thing, that is we pick up 2 elements a and b belonging to Z, and we say that A congruent to B mod M if M divides B minus A. So, as we have already seen that 14 is congruent to 14 is congruent to 28 modulo 7. But if we consider 30, what about 14 and 30? We have to take the difference of 14 and 30, which is 16, and definitely 7 does not divide 16, and hence 14 is not congruent to 13 mod 7. We write like this: suppose Z is the set of integers and M is a positive integer. For any A comma B belonging to Z, we write A, then this symbol B mod M, well, which we read as A is congruent to B modulo M if and only if M divides B minus A. Now, we take up another example. Let us consider M equal to 5. Now, we pick up the integer 1 and we pick up the integer 6. If we consider 1 and 6, then we will see that 1 is congruent to 6 modulo 5, but we can go one step forward. We can say that I would like to know all the integers which are congruent to 1 modulo 5. Can we find it? Yes, we can find it, as we see that we have 1 over here and we add 5 to it, then we have 6, then we add another 5 to it, then we have 11, then 16 and so on, and we subtract 5 to it, we get minus 1 minus 4, then we subtract 10 to 1, we subtract 10 from 1 to get minus 9 and so on. Therefore, we will get this. So, we can in fact write a general general formula that we will see over here. Here our M is equal to 5 and then our element x we are taking as 1. So, I want to know all the elements which are congruent to 1 modulo 5. So, all these elements will form a set. That set I am denoting by square bracket 1. I am writing this as set of all the elements in Z congruent to 1 modulo 5. Then what are these elements? In general, if we consider an element in this way, 1 plus n times 5, where n belongs to Z, we will get all the elements in this way by changing the values of n. For example, when n equal to 0, we get 1, when n equal to 1, we get 6, when n equal to 2, we get 11, when n equal to 3 we get 16, when n equal to 4 we get 21, and so on. When n equal to minus 1, what we have to do is 1 minus 1 plus minus 1 5. So, 1 minus 5, this is minus 4. When n equal to minus 2, this is 1 plus minus 2 into 5, this is 1 minus 10, this is minus 9. N equal to minus 3, 1 plus minus 3 into 5, that is 1 minus 15, which is equal to minus 14. N equal to minus 4, 1 plus minus 4 5. So, this is minus 20. So, I get minus 19. A part of this listing we have already seen in the previous slide. We can extend this, we can say that okay, now I want to know all the elements which are congruent to 2 modulo 5, and this set we will write this. The elements of this set can be generated from the formula 2 plus n into 5. When n equal to 0, 2 plus 0 into 5 gives me 2. When n equal to 1, 2 plus 1 into 5 gives me 7. When n equal to 2, 2 plus 2 into 5 gives me 12, and so on. When n equal to minus 1, I get 2 plus minus 1 times 5, which is 2 minus 5. So, it is minus 3. When n equal to minus 2, I get 2 plus minus 2 into 5, which is equal to 2 minus 10, which is minus 8. And we can see that all these elements are congruent to 2 modulo 5, and in fact, we can see something more, that if we pick up elements, any 2 elements from this listing, they will be congruent to each other modulo 5, and if we pick up elements from this different listing, for example, from one from here and one from here, then we will see that these elements are not congruent to each other modulo 5. We will see this thing in more details in later lectures. Now, we come to operations on relation. As we have already seen that a relation is after all a subset. Now, we have a relation from A to B, therefore, it is a subset of the Cartesian product of A and B, that is A cross B. And since it is a subset of A cross B, if we take several relations from A to B, these subsets will interact with each other through the set theoretic operations. The most common set theoretic operations that we have are union, intersection, and complementation. So, if we have 2 relations from A to B, in other words, we have 2 relations, 2 subsets of A cross B, of course, we can take the union of these 2 subsets. So, we can suppose we have 2 relations, we denote by R1 and R2 from A to B, we can consider R1 union R2. Similarly, we can also consider R1 intersection R2, and given any relation, let us say R1, we can consider its complement. Now, if we translate this to see what happens to these relations. So, if we have two relations R and S from A to B, again that means two subsets of A cross B which we are denoting by R and S, the A which is an element of capital A and small b which is the element of capital B, A is related to B with respect to the relation R union S if and only if A is related to B or A is related to B through S. I repeat again, A is related to B through the relation R union S if and only if A is related to B through the relation R or A is related to B through the relation S. A is related to B through the relation R intersection S if and only if A is related to B through R and A is related to B through S. And if we consider the unary operation complementation on the set R, that is the relation R. So, we have R bar which is the R complement, A related to B through the relation R bar if and only if the ordered pair A B is not in R, that is A is related to B through R bar if and only if A is not related to B through R. Let us look at some examples of operations on relations. Now, we have again a set A which is which consists of 1, 2, 3, 4, and we have a relation R on A, that is a relation on from A to A, that is a subset of A cross A given by the ordered pair 1 2, 1 3, 1 4, and another relation S again on A given by the ordered pair 1 2, 2 3, 4 4. Then A R union S is the simple set theoretic union of these two subsets of A cross A. If we take the union, we will see that it is the ordered pair 1 2, 1 3, 2 4, 2 3 and 4 4. Similarly, we can consider the relation R intersection S, and then we have to search for the common elements in R and S. We see that this 1 2 is common in both R and S, whereas there is no other element which appear both in R and S. Therefore, R intersection S is simply 1 2, and if we would like to know the complementation, we will have to take the set theoretic minus, in short a set minus. So, we have to take the whole set of Cartesian product of A and take the set minus R, that is the set of all elements that are in A cross A, but not in R, and then we will get the relation R bar. Next, we will come to the another way of combining relation which we call composition of relations. Suppose R is a relation from A to S. Suppose R is a relation from A to B and S is a relation from B to C. for a small a belonging to A and small c belonging to C, we will say that A is related to C by the relation R composition S if and only if there exists B belonging to capital B such that A is related A R B, that is A is related to B through R and B is related to C through R. Here we have a set A, this is a set A, and we have a set B, this is a set B, and we have another set C. We have a relation from A to B which we denote by R, another relation from B to C which we denote by S. So, R is a subset of A cross B and A is a subset of B cross C. We are trying to define a relation which we denote by R composition S. Suppose we have an element A in capital A and an element C in capital C. We will try to start from A and try to relate it to some element in B. Suppose it is related to the element small b in capital B, and suppose it happens that this small b again is related to C in capital C, then we say that A is R composition S C. This gives us the definition that since there exists B belonging to capital B such that A are B and B are C. Now, if it so happens that A is related to something here, but let us say B dash, and this is related to nothing, this is this is not related to anything over here, then there is then A is not connected to any element in C. So, A is not related to any element in C, or it may so happen that we have an element, let us say A dash in capital A and C dash in C such that there is no element in B with the property that A dash is related to that element and that element is related to C. Then we will say that A is not related to C dash. Now, what we can do is that it is not necessary that A, B, C are distinct. A, B, C may be same as written here. Suppose A equal to B equal to C. So, all of them, all B, C, we are writing them as A. So, we can compose a relation on A, that is A to A, over and over again. So, we will write R raised to the power n as R composed, R composed, R composed and so on, composed R n times. For example, if it is R square, it is R composition R, if it is R cube, it is R composition R composition R. So, in this way we can define powers of relations. Let us look at some examples. Again we consider the set 1, 2, 3, 4 and relation on A which is given by 1, 2, 1, 3, 2, 4, and another relation S which is given by 1, 2, 2, 3 and 4, 4. yeah, and then we have to find out the relation. So, let me write down the relation A. Okay. So, we have A equal to 1, 2, 3, 4, R equal to 1, 2, 1, 3, 2, 4 and S equal to, let us quickly go back, 1, 2, 2, 3, 4, 4, 1, 2, 2, 3 and 4, 4. Then we have to compute R composition S. How to do that? I start with 1, I have written 1 over here, I go to 2, yes, 1 is related to 2. Now, we see in S whether 2 is related to anything, yes indeed 2 is related to 3. So, I write 1 3, 1 3 is an element of R composition S. Now, is there anything else? No, 1 going to 2, but 2 is related to only 3 in S. Now, we come to 1 goes to 3, 1 goes to 3, then I ask a question, let us cancel this. So, I write only 1 here, 3 is my intermediate element and we see whether 3 is somewhere in S, 3 is nowhere in S. So, it does not appear in R composition S. Now, I come to 2. Now, 2 is related to 4 and 4 is related to 4. So, 2 4 will appear in R composition S. Therefore, R composition S will have only 2 elements, 1 3 and 2 4, which we have over here. So, this is all about today. Thank you.